Welcome to The Explainer. Today, we're diving into one of the absolute most fascinating frontiers in tech, how artificial intelligence actually acts like a digital detective to deduce logic, verify facts, and, well, ultimately try to make sense of human language. Let's kick things off with a pretty wild puzzle that researchers have been trying to solve for decades. How do we teach a machine not just to read words on a screen, but to truly read between the lines? Like a human investigator. When you or I read a sentence, we instantly grasp all that unwritten context. But for a machine, that requires a highly specific, totally mathematical approach to logic. So here's our game plan for today. First, we'll look at the machine logic puzzle. Then, the 3 rules of inference. After that, why this matters today, followed by the evolution of AI logic. And finally, we'll wrap up with training the AI detective. All right, part 1. The machine logic puzzle. Let's crack open our very first case file. In the world of natural language processing, NLP, this core challenge is known as Natural Language Inference, or Textual Entailment. It's essentially the AI's way of evaluating information. The AI looks at a piece of evidence, which we call the premise, and a subsequent claim, which we call the hypothesis. Its entire job is to figure out the precise relationship between those 2 pieces of text. Think of the premise as the indisputable facts of a crime scene. It's the baseline text that we know is absolutely true. The hypothesis, on the other hand, is the detective's working theory that needs to be rigorously checked against those facts. The AI literally has to ask itself, based only on this premise, what can I deduce about the hypothesis? Moving on to part 2, 3 rules of inference. Now, every good detective needs a framework, right? We're going to use a super simple, relatable example here of a sleeping cat. Applying the exact same premise to 3 different hypotheses gives us our 3 core categories: entailment, contradiction, and neutral. Let's break down exactly what the AI is thinking in each of these scenarios. First up, we've got entailment. This happens when the truth of the premise absolutely guarantees the truth of the hypothesis. If our hard evidence, our premise, states the cat is sleeping, well, it absolutely guarantees the hypothesis that there is a cat. Boom. The AI can confidently lock this in as a proven logical inference. Conversely, a contradiction means the AI essentially catches a lie. If the indisputable premise is the cat is sleeping, it mathematically guarantees that the claim the cat is playing is false. The AI recognizes there is no way these 2 states can exist simultaneously based on the info provided, so it refutes the hypothesis. Now, the neutral state, that's often the trickiest one for AI. The premise, the cat is sleeping, neither guarantees nor refutes the hypothesis that the cat is dreaming, even if we can see its little paws twitching. The AI has to be smart enough to recognize that it simply lacks the evidence to make a definitive call either way. It actually has to sit comfortably in the unknown. Which brings us to part 3, why this matters today. So, you might be wondering, how does this whole feline logic puzzle translate into the tech you use every single day? Well, this deduction capability is absolutely crucial. It's the invisible engine powering your daily tools. In question answering, it validates that the answer an AI gives actually addresses your prompt. For information retrieval, it's what ensures your search engine results are actually relevant to your query. It's used in information extraction to check consistency against source content, and it evaluates machine translation to guarantee that when you translate a web page, the core meaning isn't lost. Honestly, this is exactly what stops AI from just hallucinating confident-sounding nonsense. Let's jump into part 4, the evolution of AI logic. So how exactly did we build this digital detective over time? Well, the approach really evolved over 3 distinct eras. Era 1 relied heavily on feature-based models. These were basically handcrafted rules that mostly just checked if the exact same words appeared in both sentences. Then, Era 2 brought us deep learning, specifically recurrent neural networks, or RNNs, using memory models like LSTMs to read text sequentially and actually capture some context. But then, Era 3 absolutely changed the game with transformers, bringing us modern powerhouse models like BERT and RoBERTa. These modern transformer powerhouses achieve this logic through a highly structured architecture. First off, they use multiple self-attention layers to capture deep context. Second, they undergo massive pre-training on enormous bodies of text, using masked language modeling. If you're not familiar, that's essentially training the AI by making it play high-stakes fill-in-the-blanks with missing words. Finally, they get fine-tuned specifically on natural language inference datasets. BERT, for instance, uses a specific classification token, the CLS token, to generate a final mathematical representation of the sentence pair and ultimately deliver its verdict. Totally crucial to this modern approach is the attention mechanism. You can really just think of this like a digital magnifying glass. It's a weighting scheme that allows the AI to dynamically focus on the most relevant parts of the text, rather than treating every single word equally. This is the secret sauce that allows the model to understand those complex intertextual relationships and dependencies between the premise and our hypothesis. All right, our final section, Part 5, Training the AI Detective. Now, AI models aren't just born smart, right? They have to be rigorously tested. The Stanford Natural Language Inference dataset, or SNLI, provides the foundational annotations for this. Then we have MultiNLI, which expands the AI's scope across really diverse textual genres, making sure it isn't just good at reading one specific type of writing. And finally, the Recognizing Textual Entailment, or RTE challenge sets. These are annual datasets designed specifically to push the boundaries and test the AI on weird edge cases. Just to put the sheer scale of this training into perspective for a second, that foundational SNLI dataset alone contains over 500,000 sentence pairs. And the crazy part? Those aren't machine-generated. They're crowdsourced with real human annotations. It takes a literally incredible amount of human logic to map out these training grounds, just so the machine can eventually learn to mimic our exact deduction process. Which brings us to our final takeaway. As we start to rely more and more heavily on these brilliant digital detectives to run our search engines and power our translation tools, it leaves us with a really profound thought about the true nature of machine comprehension. I mean, think about it. If a model like BERT can perfectly navigate 500,000 logical relationships, does it actually understand meaning? Or has it simply mastered the math of probability? It's a massive question, and one the field of AI is going to be wrestling with for years to come. Thanks so much for joining me on this explainer.